Something happened on June 23, 2025, that most of the world quietly ignored. A machine opened its eye for the very first time, and in just 10 hours it saw more of the universe than humanity had collectively observed in centuries. No headlines prepared you for what this actually meant. No news channel explained what was truly unlocked that night. Because what the Vera C. Rubin Observatory captured in those first images was not just light from distant stars. It was the opening frame of the most consequential story ever told. A decade-long investigation into the 95% of reality that science still cannot explain. There's a mountain in northern Chile, rising 2,182 meters above sea level, where the air is so dry and the sky so dark that the stars do not twinkle. They burn. They hold perfectly still in the blackness like frozen fire, undisturbed by the moisture and light pollution that blinds every other telescope on Earth. This mountain is called Cerro Pachon, and perched at its summit, shaped like a great concrete sphinx against the dying blaze of each sunset, sits a structure that took more than 2 decades, and the combined will of 28 nations to build. 28 countries had a hand in commissioning this telescope, and when its first images were unveiled, watch parties erupted across 6 continents. Think about what that means. Not a rocket launch, not a moon landing. A telescope showing its first photographs, and the world stopped to watch. The machine is called the Vera C. Rubin Observatory. And what it has just begun doing will change not just astronomy, but the foundational understanding of what the universe is actually made of. But here is where most people make their first mistake. They assume this is a story about beautiful space photography. It is not. This is a story about a problem so enormous, so deeply unsettling, that the greatest scientific minds on the planet have spent decades refusing to admit how badly they are losing to it. And Rubin was built to finally force a confrontation. The problem is this: everything we know, galaxies, stars, planets, our families, friends, and even the ground beneath our feet, makes up just 5% of the universe. The remaining 95% is composed of mysterious components that scientists call dark energy and dark matter. Read that again, 5%. Everything that has ever been discovered, measured, photographed, theorized, named, or explored in the entire history of human science accounts for 1/20th of what actually exists. The rest is invisible, undetectable by conventional means, and poorly understood to a degree that should be deeply alarming to anyone paying attention. We are not missing a small piece of the cosmic puzzle. We are missing the puzzle itself, and only holding the frame. Dark matter makes up approximately 27% of the universe. It does not emit light, does not reflect light, does not interact with light in any way that our instruments can currently catch. And yet it must be there, because without it, galaxies would fly apart. The stars within the Milky Way rotate at speeds that make no gravitational sense unless something invisible, something massive, is holding the entire system together like an unseen hand. Vera Rubin herself, the legendary American astronomer for whom this observatory is named, was among the first scientists to prove this mathematically in the 1970s. She measured the rotation curves of galaxies and found an irreconcilable contradiction between what the visible mass should produce and what was actually happening. She was largely dismissed for it. She was right. And now, decades after her death, the telescope that bears her name has opened its eye to finish what she started. Then there is dark energy. That's the other 68%, which is stranger still. Dark energy is thought to be responsible for the universe's accelerating expansion. But what these invisible phenomena are made of is barely understood. The universe is not just expanding, it is expanding faster and faster, as if something is pushing it apart from the inside, accelerating the separation of galaxies at a rate that contradicts almost every model physicists built in the 20th century. What is causing this acceleration? No one knows. What is dark energy made of? No one knows. How will it behave in 1 billion years? Will it slow down? Will it stabilize? Or will it eventually tear apart every atom in existence in what cosmologists call the Big Rip? No one knows. And this is where Rubin enters the story. Not as a solution, but as humanity's most sophisticated attempt yet to stop not knowing. The NSF-DOE Vera C. Rubin Observatory team revealed the first images from the world's newest and most powerful survey telescope on June 23, 2025, at an event in Washington, D.C. Those first images were not a final product. They were a proof of capability, a demonstration that the machine worked, that the optics were aligned, that the camera was functioning, and that the data pipeline was flowing. But even as a test, what Rubin captured in those early hours was staggering. In just over 10 hours of test observations, Rubin Observatory had already captured millions of galaxies and Milky Way stars and thousands of asteroids. 10 hours. The Hubble Space Telescope required 11 days of continuous pointing at a single patch of sky to capture its famous deep field image. Rubin did something comparable in magnitude across a vastly larger field of view in less than half a day. And it was not even trying yet. The camera at the heart of this machine deserves its own moment of consideration, because nothing like it has ever existed. The telescope features an 8.4-meter primary mirror and the world's largest digital camera at 3.2 gigapixels, 3,200 megapixels. For context, the camera on a high-end modern smartphone delivers around 50 megapixels. Rubin's camera delivers 64 times that resolution. And it does so across a field of view so wide that it captures an area of sky equivalent to roughly 45 full moons simultaneously. The full resolution images demonstrate the true power of this 3,200 megapixel camera. A single image from this device is about the size of a basketball court if it were filled with Ultra HD televisions. No single screen on Earth can display one of these images at full resolution. They have to be navigated like a map, zoomed into like a satellite view of a city, where pulling in close reveals not just stars, but the ghost light of ancient galaxies hiding behind them, fainter than anything previous surveys could detect. But here is where it gets more interesting and more consequential. The first images were not what Rubin was built for. They were the opening credits. What Rubin was actually designed to do is something that no telescope in history has ever attempted at this scale. It was built to watch the sky change, not to take a single photograph of the universe as it is, but to take the same photograph over and over night after night for 10 years and measure every difference between each frame. The legacy survey of space and time will scan the sky nightly for 10 years to precisely capture every visible change. The result will be an ultra-wide, ultra-high-definition time-lapse record of the universe, a movie of the cosmos. The greatest movie ever made, not by any director, but by physics itself. And Rubin is the camera rolling on an open shutter for a decade. And this is where everything changes. Because when you watch the sky change, you do not just see what is there. You see what appears, what disappears, what moves, what explodes, what pulses with hidden rhythm, what was invisible last week and is burning bright tonight. The universe, it turns out, is not a static painting. It is a violent, restless, constantly shifting system of events. And the only reason we thought it was quiet was because our previous telescopes could only afford to look at one small piece of it at a time. Rubin watches all of it simultaneously, every night, without blinking. In just a month and a half of early optimization surveys, before the main mission had even formally started, Rubin discovered over 11,000 never-before-seen asteroids, including 33 near-Earth objects and 380 trans-Neptunian objects. In 6 weeks of warm-up exercises, this telescope found 11,000 rocks in space that humanity had never cataloged before. 33 of them qualify as near-Earth objects, meaning their orbits bring them into the neighborhood of our planet. This is not a minor footnote. Planetary defense depends on knowing where these objects are. The better our asteroid catalog, the better our early warning systems, the better our chances of identifying a genuinely threatening object with enough time to actually do something about it. And Rubin, operating at full capacity over 10 years, is expected to close most of the remaining detection gap for asteroids in the 50 to 300 meter range, the category of objects large enough to level a city or trigger a regional catastrophe. Think about what that means in practical terms. Right now, there are asteroids orbiting the Sun whose existence we do not know about. They are real. They are moving. Some of them cross Earth's orbital path, and we cannot see them because our current surveys simply do not look fast enough, wide enough, or deep enough to find them all. Rubin changes that equation permanently. By the time its 10-year survey concludes, the solar system will be mapped with a completeness that was previously theoretical. We will know what is out there in a way we simply do not today. But asteroids are only one thread in a tapestry of scientific objectives that Rubin carries. There is also the question of Planet 9. The hypothetical massive world that astronomers have theorized for years is lurking in the extreme outer reaches of the solar system, far beyond Neptune, large enough to be warping the orbits of distant trans-Neptunian objects through its gravitational influence. The Vera C Rubin Observatory has officially entered its operational phase, and one of its most anticipated objectives is the direct detection of Planet 9. This hypothetical massive world is believed to lurk in the extreme outer reaches of the solar system, far beyond the orbit of Neptune. No telescope has been able to confirm or deny Planet 9's existence because it would be extraordinarily faint, a frozen, distant world reflecting barely any sunlight at the edge of the solar system. But Rubin's combination of wide field coverage and extreme sensitivity means it will scan the outer solar system more thoroughly than any previous instrument. If Planet 9 exists, Rubin will find it. If Planet 9 does not exist, Rubin will prove that too, and the scientific community will have to return to the drawing board and explain why the outer solar system's orbital mechanics are behaving as they are. Then there are supernovae, the violent deaths of massive stars that, for a brief period, outshine entire galaxies. Rubin will catch these explosions in real time, watching stars that were stable the night before suddenly detonate with the force of 100 billion suns. Because it watches the whole sky repeatedly, It will catch supernovae at every stage of their evolution, from the first flash to the long fade, building a data set of stellar explosions that will fundamentally advance the understanding of stellar physics. And supernovae are not just spectacular, they are essential cosmological tools. Type Ia supernovae are used as standard candles to measure cosmic distances, which is precisely how astronomers first discovered that the universe's expansion is accelerating. More supernovae data means more precise measurements of that acceleration, which means better constraints on the nature of dark energy itself. And here's the layer of the story that most coverage has not explained properly. A primary science goal of the legacy survey of space and time is constraining dark energy through weak gravitational lensing of the large-scale structure of the universe. After a full year of data from LSST, these measurements are expected to reach precision, comparable to recent results from the Dark Energy Spectroscopic Instrument, providing an independent test of hints that dark energy may evolve over time. This sentence contains something genuinely explosive if you understand what it is saying. There are current hints, emerging from multiple independent experiments, that dark energy may not be a fixed constant of physics. It may be changing. It may have been stronger in the early universe and weaker now, or vice versa. If that is true, it invalidates the cosmological constant that has sat at the center of the standard model of cosmology for decades. It means the equations are wrong, and it means the ultimate fate of the universe, which those equations are used to calculate, is not what we think it is. Rubin will test this. It will measure the shapes of hundreds of millions of distant galaxies and detect the subtle distortions caused by dark matter warping the path of their light across billions of light years of space. These distortions are so small that they are completely invisible to the naked eye. The galaxies just look slightly stretched or compressed in ways that require statistical analysis of enormous samples to detect. But when you have hundreds of millions of galaxies to analyze, the statistics become powerful enough to map the invisible distribution of dark matter across the observable universe with a precision never before achieved. With Rubin's wide field of view and high resolution, the subtle distortions of galaxy shapes caused by dark matter will be detectable, allowing scientists to map dark matter and explore its cosmic tug of war with dark energy. A tug of war. That is precisely what it is. Dark matter holds the universe together, pulling matter into galaxies, galaxies into clusters, clusters into the vast cosmic web of filaments and voids that gives the universe its large-scale structure. Dark energy pushes back, stretching space itself, trying to drive everything apart. The universe we inhabit exists because of the current balance between these two invisible forces, and we do not understand either of them at a level that should give anyone comfort. Rubin will spend the next decade mapping that battle in real time, measuring which force is winning, how the balance has changed over cosmic history, and what the final outcome is likely to be. The LSST officially launched on June 30th, 2026, unleashing a nightly stream of up to 7 million alerts, notifications dispatched every single night to astronomers around the world, flagging every detected change in the night sky. 7 million alerts per night. Consider what that number represents. Every asteroid that moved a fraction of a degree from where it was yesterday, every star that brightened unexpectedly, every galaxy that flickered, every supernova that ignited, every object that appeared where nothing was cataloged before. All of it detected, analyzed, and broadcast in near real time by a software pipeline built at the University of Washington that processes the raw data from Cerro Pachon in 60 seconds. An image is taken. 60 seconds later, it is compared against previous images of the same sky region. Differences are identified, and alerts go out to observatories around the world so that other telescopes can follow up immediately. Rubin is not just a telescope. It is an early warning system for the entire astronomical community, functioning as the front line of a global network that can respond to cosmic events as they happen. Rubin's first released composite image, titled The Cosmic Treasure Chest, was compiled from 1,185 individual exposures. The most notable aspect of the image is that instead of the usual dark void between objects, the entire field of view is brimming with details thanks to the observatory's ultra-sensitivity. That phrase, the usual dark void, is important. When other telescopes photograph the sky, there is black space between the stars and galaxies, empty, featureless. Rubin fills that emptiness. What looked like void turns out to be populated with faint galaxies, with gossamer clouds of interstellar gas, with the ancient light of objects so distant that the photons arriving at the camera have been traveling since the universe was less than 1 billion years old. There is no void. There never was. There was only instruments that were not sensitive enough to see what was always there. The first image of the Lagoon Nebula and the Trifid Nebula, one of Rubin's celebrated early captures, was built from 678 individual images taken in just over 7 hours of observing time. Combining many images in this way clearly reveals otherwise faint or invisible details, such as the clouds of gas and dust comprising the Trifid and Lagoon nebulae, which are several thousand light years from Earth. Gas clouds that are invisible in a single exposure emerge from the noise when hundreds of frames are stacked. Faint stars behind thick dust reveal themselves. The universe becomes more populated, more complex, more layered with every additional photon captured. And Rubin will capture an almost incomprehensible quantity of photons over the next decade. When the survey concludes in the mid-2030s, the final dataset, billions of objects, trillions of measurements, will be made available not only to professional astronomers worldwide, but to the general public. This is a detail that deserves far more attention than it receives. The entirety of what Rubin discovers, every asteroid, every supernova, every dark matter measurement, every variable star, every distant galaxy cataloged for the first time, will be publicly available, not locked behind institutional paywalls, not reserved for affiliated researchers at partner universities. Open, free, available to anyone on Earth with an internet connection and the curiosity to look. High school students in Karachi will be able to query the same database as cosmologists at MIT. Amateur astronomers in rural communities will have access to data that would have required a billion-dollar telescope budget just 20 years ago. This is an act of scientific democratization that has no historical precedent at this scale. But the deeper story, the one that should sit with you long after this ends, is not about the data. It is about what the data might tell us. During the next decade, LSST will be able to confirm or dispute if tensions seen today in cosmological data are due to new physics. New and unexpected phenomena could confirm or disrupt our current understanding of the universe. New physics. That phrase, in the mouth of a scientist, carries an almost unbearable weight. It means the equations we use to describe reality are not merely imprecise. They may be wrong at a fundamental level. There are tensions in current cosmological measurements that do not resolve cleanly. The Hubble constant, and the number that describes how fast the universe is expanding, gives different values depending on how you measure it. Early universe measurements and late universe measurements disagree. Either something is wrong with the measurements, or something is wrong with the model. If Rubin's data confirms that dark energy is evolving, that it is not a constant, but a dynamic field that changes over time, the model breaks, and what replaces it is currently unknown. LSST could also discover quite a few exoplanets, worlds orbiting other stars, in places where other telescopes have difficulty, such as in densely packed star clusters and even within our Milky Way's companion satellite galaxies. That last possibility is almost too extraordinary to process. Our planets in other galaxies, not in our galaxy, in other galaxies entirely hundreds of thousands of light years away. If Rubin detects the gravitational signatures of planets orbiting stars in the Magellanic Clouds, it will be the first evidence of planetary systems beyond the Milky Way. A discovery that will redefine the scope of the question, is there life in the universe? Stellar streams are like strings of pearls, whose stars trace the path of a system's orbit and have a shared history. If we find a pearl necklace with a few scattered pearls nearby, we can deduce that something may have come along and broken the string. Those breaks in stellar streams are signatures of dark matter, clumps passing through, invisible concentrations of mass that we cannot see directly, but whose gravitational footprints we can read in the disrupted paths of stars. Rubin will find these disruptions by the thousands, building the first comprehensive map of dark matter, distribution across our galaxy at multiple scales, from the largest cosmic filaments down to the smallest substructure. This is not an incremental improvement. This is the difference between having a blurry satellite photograph of a city and having a street-level map of every alley. The technical challenges Rubin had to overcome to reach this point are worth understanding, because they reveal the ambition of what was built. When a photon in Rubin's path reaches Earth from some distant celestial body, it first hits its 8.4-meter primary mirror. That photon then bounces to a smaller secondary mirror and an even smaller tertiary mirror housed within the primary. The primary mirror itself has traveled more than 11,000 kilometers from Arizona to the summit of Cerro Pachon, where it was coated with silver in a large, sparse area of the observatory that acts as an on-site factory. A mirror the size of a small swimming pool, transported across thousands of miles, coated in silver in a controlled environment at the top of a Chilean mountain, aligned with nanometer precision to capture light that has been traveling for billions of years. The engineering audacity required for this is matched only by the scientific ambition behind it. After each quick image analysis, the files are sent through a dedicated undersea fiber optic cable that goes from Cerro Pachon to the survey database at SLAC, the Stanford Linear Accelerator Center in California, which processes and stores the data. Every night, terabytes of information travel from a mountaintop in the Atacama Desert beneath the Pacific Ocean to a data center on the U.S. West Coast, where algorithms developed over years of preparation sort through millions of detected objects in near real time. The pipeline is itself a marvel of engineering. built to handle a data throughput that has no parallel in civilian science. And what makes all of this more urgent, more charged with a kind of civilizational stakes, is the context in which Rubin is now operating. The Rubin Observatory is jointly operated by the National Science Foundation and the Energy Department, which have experienced significant turbulence related to research funding during the second Trump administration. This telescope, representing more than 2 decades of sustained scientific investment, continues operating in an environment of institutional uncertainty. The science does not pause for politics. The universe does not wait for budget debates. But the humans who built this instrument and the institutions that fund its operation exist in a world where long-term scientific commitments are increasingly fragile. Rubin is, among other things, a test case for whether democratic societies can sustain multi-decade commitments to fundamental research that will not pay dividends for years or decades, or perhaps never in any conventional economic sense. For astronomers, the next 10 years will be anything but routine. Rubin will feed generations of scientists with trillions of data points of billions of objects. Explore the data, harvest it, develop your idea, see if it's there. It's going to be phenomenal. That is the voice of the observatory's own technical leadership. Not hype, not marketing. A scientist who has spent years building this instrument telling you what he believes it will do, and what it will do is generate scientific careers. It will define the research agenda of an entire generation of astronomers. The discoveries made from LSST data will be the subject of doctoral theses that have not been written yet, by students who have not yet entered university, answering questions that have not yet been precisely formulated. One of the scientists most excited about what Rubin will find is most interested to see if LSST discovers Planet 9, a hypothesized planet 5 to 10 times more massive than Earth that may be warping the orbits of outer solar system bodies. Even if Rubin cannot spot the exact planet, it could detect more objects with warped orbits pointing to Planet 9's existence. And even a null result, finding nothing, would be an important nail in yet another planetary theory. That is what scientific integrity looks like in practice. A null result, no detection, no planet, is still a result. It still eliminates a hypothesis. It still moves understanding forward. Rubin will produce definitive answers or definitive non-answers. And in science, those are equally valuable. The scale of what Rubin has begun is difficult to hold in the mind all at once. When the LSST is complete, the final dataset will contain billions of objects with trillions of measurements, all accessible through regular data releases. Billions of objects, trillions of measurements. Over 10 years, across the entire southern sky, revisited every 3 days, 6 color filters, 7 million alerts per night. The total data volume, when the survey concludes, will approach 500 petabytes, roughly equivalent to 500 million gigabytes. The sum of human digital knowledge, from the first web page to the present, is estimated at a few zettabytes. Rubin will add to that total in the domain of astrophysical observation in a way that is genuinely unprecedented. And all of it, every byte, will eventually be publicly released. What are we really looking at when we look at what Rubin is doing? We are looking at humanity's most serious attempt to answer the most serious questions it has ever faced about the nature of reality. Not philosophical questions, empirical ones. Is dark matter a particle? Is dark energy a field? Is the universe's expansion accelerating in a way that points to eventual dissolution? Are the physical constants of the universe truly constant? Or do they change slowly across cosmic timescales in ways that would render our physical laws local approximations rather than universal truths? These are not abstract puzzles. They are the architectural questions of existence. The answers will shape physics, mathematics, engineering, and philosophy for as long as civilization endures. And right now, tonight, as you are reading or listening to this, a 350-ton telescope on a Chilean mountaintop is turning its 8.4-meter eye to the southern sky, opening its 3,200 megapixel shutter, and capturing light that has been traveling across the void for billions of years. It is doing this automatically, with minimal human intervention, processing what it sees in 60 seconds, sending alerts to astronomers across the planet. And it will keep doing this every clear night for the next 10 years, until it has seen more of the universe than all previous surveys in history combined. The real question is not what Rubin will find. The real question is whether we are ready for the answer. Because somewhere in that ocean of data, in the shape of a galaxy, in the disruption of a stellar stream, in the light curve of a distant supernova, in the slow drift of an object at the edge of the solar system, the universe has buried something. A signal, a fingerprint, a clue to what 95% of everything actually is, and Rubin is hunting it with more sophistication and more patience than anything humanity has ever built. What happens when the clue is found? What happens if dark energy is evolving and the standard model breaks? What happens if Planet 9 is real? What happens if, in the galactic archaeology of stellar streams and ancient light, we find something that does not fit any model we currently have? Something genuinely new, a cosmic phenomenon that rewrites the physics textbooks? The answer is, we will not be ready. We never are. The universe does not brief us in advance. It does not warn us before it overturns our assumptions. It just keeps existing, vast and indifferent, hiding 95% of itself in plain sight. And for the next 10 years, one machine on one mountain in Chile will be the closest thing we have to an answer. Whatever it finds, nothing will be the same afterward.